Hello and welcome to a Performance Tuning Deep Learning Models Masterclass. My name is Mike West and I'll be your instructor for this class. Modern open source libraries like TensorFlow and Keras have become the gold standard for developing neural network models. These frameworks and libraries have revolutionized this space. Gone are the days when you might spend weeks debugging the translation of poorly documented mathematics into code in the hopes of getting even the simplest model running. Today, using libraries like Keras and frameworks like TensorFlow, defining and fitting multi-layer perceptrons can be done in minutes. While defining and fitting models has become easier, getting good performance with a neural network model on specific problems remains challenging. Traditionally, configuring neural networks to get good performance was referred to as a dark art. This is because there are no clear rules on how to best prepare the data and configure a model for a given problem. Neural networks have been used in academia and industry for decades now, and there are a suite of standard techniques, tips, and configurations that you can use to greatly increase the likelihood of getting better than average performance from a neural network model. I've created this course to pull together the best classical and modern techniques in order to provide you with a playbook that you can use to get better performance on your next project using deep learning neural networks. In the course, we're going to focus on three main things. The first one is better learning. You're going to discover the techniques to improve and accelerate the process used to learn or optimize the weights of neural network models. Secondly, better generalization. You're going to learn about techniques used to reduce overfitting of the training dataset to improve the generalization of models on new data. And thirdly, better predictions. You're going to learn about techniques to improve the performance of the final model when used to make predictions on new data. Thank you for your interest in this course, Performance Tuning Deep Learning Models Masterclass, and we'll see you in the course. Let's talk about what you're going to learn in this hands-on course on performance tuning with deep learning models. This course is results-driven. You're going to learn how to get results as a machine learning engineer practitioner to get the most out of your deep learning models on your own predictive modeling projects. Techniques are demonstrated in the context of small, well-understood predictive modeling programs and multi-layer perceptron neural network models, but can easily be applied to a wide range of problems and with a suite of different types of neural network models. Let's cover a few things you'll learn. You're going to learn how to accelerate learning through better configured stochastic gradient descent batch size, loss functions, learning rates, and how to avoid exploding gradients via gradient clipping. You're going to learn how to accelerate learning through correct data scaling, batch normalization, and the use of modern activation functions such as a rectified linear activation function. You're going to learn how to deal with the problem of overfitting and a tour of regularization techniques. You're going to learn how to reduce overfitting by updating the loss function using techniques such as weight regularization, weight constraints, and activation regularization. In the course, you'll learn how to reduce overfitting using techniques such as dropout, the addition of noise, and early stopping. You're going to learn how to combine the predictions from multiple models and tour an ensemble of learning techniques. You're going to learn how to combine the predictions from multiple different models using techniques such as weighted averaging ensembles and stacked generalization ensembles, also known as blending. Lastly, you're going to learn how to combine the predictions from multiple models saved during a single training run with techniques such as horizontal ensembling and snapshot ensembling. Again, I'd like to thank you for your interest in this hands-on course on performance tuning with deep learning models, and let's get started. Before you get started, let's make sure you're in the right place. This course was created for developers that know some applied machine learning and some deep learning. Maybe you want or need to start deep learning on your research project or on your project at work. This course was created to help you do that quickly and efficiently by compressing years of knowledge and experience into a laser-focused course of hands-on tutorials. The course does make a few assumptions about you. You know your way around basic Python for programming. Number 2, you know your way around the core Python machine learning libraries like NumPy, scikit-learn, and pandas. Number 3, you know your way around Keras for deep learning. And lastly, you have a solid understanding of machine learning concepts. If you don't have all these prerequisites, don't worry. My course, the Complete Python course for machine learning engineers, will provide you with all the Python and library skills you need to understand to get the most out of this course. If you have a solid base in the foundations of machine learning and Python, and you're interested in getting the most out of your deep learning models, then this course is for you. All right, in this lesson, let's talk about a framework for optimal deep learning. Unfortunately, you can't efficiently grid search across all the techniques used to improve deep learning performance. They uniquely change aspects of the training data, learning process, model architecture, and more. Instead, you're going to need to diagnose the type of performance problems you're having with the model, then carefully choose and evaluate a given intervention specific to the problem at hand. There are three types of problems that are straightforward to diagnose with regard to poor performance of a deep learning neural network model, and they are problems with learning. These are problems with the model when they can't effectively learn a training dataset or show slow progress or bad performance when learning the training dataset. Problems with generalization. These generalization problems manifest in a model that overfits the training dataset and makes poor performance predictions on the holdout dataset. Problems with predictions. Problems with predictions manifest in the stochastic training algorithm having a strong influence on the final model, causing a high variance in behavior and performance. This framework provides a systematic approach to thinking about the performance of your deep learning models. There is some natural overlap and interaction between these areas of concern. For example, problems with learning affect the ability of the model to generalize as well as the variance in the predictions made from the final model. The sequential relationship between the three areas in the proposed framework allows the issue of deep learning model performance to be isolated, then targeted with a specific technique or methodology. Let's summarize techniques that can assist you with each of these problems. First, there's optimal learning. These are techniques that improve or accelerate the adaptation of the neural network model weights in response to a given training dataset. Optimal generalization. These are techniques that improve the performance of a neural network model on a holdout dataset. Optimal predictions. These are techniques that reduce the variance in the performance of a final model. Now that you have a high-level understanding of the framework for systematically diagnosing a performance problem with a deep learning neural network, let's take a look at some examples of techniques that may be used under each of these three areas of concern. Hello and welcome back. Let's cover optimal generalization techniques in this lesson. Better generalization techniques are those that change the neural network model or the learning algorithm to reduce the effect of the model overfitting on the training dataset and improve the performance of the model on the holdout, validation, or test dataset. In this course, you're going to review the techniques to reduce generalization error of the model during training. Techniques that are designed to reduce generalization error are commonly referred to as regularization techniques. Almost universally, regularization is achieved by somehow reducing or limiting model complexity. Perhaps the most widely understood measure of model complexity is the size or the magnitude of the model weights. A model with large weights is a sign that it may be overly specialized to the inputs in the training data, making it unstable when used to making predictions on new unseen data. Keeping weights small via weight regularization is a powerful and widely used technique. So, weight regularization is a change of the loss function that penalizes the model in the proportion to the norm, the magnitude, of the model weights, encouraging smaller weights and, in turn, lowering the complexity of the model. Rather than encouraging the weights to remain small via an updated loss function, it is possible to force the weights to be small using a constraint, hence weight constraints. These update the model to rescale the weights when the vector norm of the weights exceeds a threshold. The output of a neural layer, regardless of where that layer is in the stack of layers, can be thought of as an internal representation or a set of extracted features with regard to the input. Simpler internal representations can have a regularizing effect on the model and can be encouraged through the constraints that encourage sparsity from zero values. This is called activity regularization. This is a change in the loss function that penalizes a model in proportion to the norm, the magnitude of the layer's activations, encouraging smaller and more sparse internal representations. Noise can be added to the model to encourage robustness with regard to the raw inputs or the outputs from the prior layers during training. For example, dropout. Probabilistically removing connections, weights, while training the network to break tight coupling between nodes across layers. Then there's input noise. This is the addition of statistical variation or noise in the input layer or between hidden layers to reduce the model's dependence on a specific input value. Often, overfitting can occur due to simply training the model too long on a dataset. A simple solution to this is stop training early. This is called early stopping. This is where you monitor the model performance on the holdout validation dataset during training and stop the training process when performance on the validation starts to degrade. All right, in this lesson, let's talk about optimal prediction techniques. Optimal prediction techniques are those that complement the model training process in order to reduce the variance in the expected performance of the final model. Throughout the course, you're going to review the techniques used to reduce the expected variance of a final deep learning neural network. The variance in the performance of a final model can be reduced by adding bias. The most common way to introduce bias to the final model is to combine the predictions from multiple models. This is referred to as ensemble learning. More than reducing the variance of the performance of the final model, ensemble learning can also result in better predictive performance. Effective ensemble learning methods require that each contributing model have skill, meaning that each model makes predictions that are a little better than random, but that the prediction errors between the models have a low correlation. This means that the ensemble member models should have skill, but in different ways. This can be achieved by varying one aspect of the ensemble. For example, vary the training data used to fit each member. Next, vary the members that contribute to the ensemble prediction. Lastly, vary the way the predictions from the ensemble members are combined. The training data can be varied by fitting models of different subsamples of the dataset. This might involve fitting and retraining models on different randomly selected subsets of training data, retraining models for each fold in a k-fold cross-validation, or retraining models across different samples with replacement using the bootstrap method. Collectively, you can think of these methods as resampling ensembles. A resampling ensemble is an ensemble of models that fit on different samples of the training data. Perhaps the simplest way to vary the members of an ensemble involves gathering multiple models across different runs on the training dataset. The stochastic learning algorithm will cause a slightly different fit on each run that, in turn, will have a slightly different fit. Averaging the models across different runs will ensure the performance remains consistent. Model averaging ensembles retrain models across multiple runs of the same learning algorithm on the same dataset. Variations of this approach may involve training models with different hyperparameter configurations. It can be expensive to train multiple deep learning models, especially ones where it may take weeks for the model to fit. An alternative is to collect models for use as contributing ensemble members during a single training run. For example, there are horizontal ensembles. These are ensemble members collected from a contiguous block of training epochs towards the end of a single training run. Then there are snapshot ensembles. A training run uses an aggressive cyclic learning rate where the ensemble members are collected at the trough of each cycle of the learning rate. The simplest way to combine the predictions from multiple ensemble models is to calculate the average of predictions in the case of regression, or statistical mode, the most frequent prediction in the case of classification. Alternatively, the best way to combine the predictions from multiple models can be learned are weighted average ensembles. This is also known as blending. This is where the contribution from each ensemble member to an ensemble prediction is weighted using learned coefficients that indicate the trust in each model. And then there's stacked generalization, referred to as stacking. A new model is trained to learn how best to combine the predictions from the ensemble members. All right, in this lecture, let's talk about how to use the framework. You can think of the organization of these techniques into three disparate areas: optimal learning, optimal generalization, and optimal prediction as a systemic framework for improving the performance of your neural network model. Now, there are too many techniques to reasonably investigate and evaluate in each one of your projects. Instead, you're going to have to be a little methodical and then use the techniques in a targeted way to address the defined problem. So let's talk about the steps. So step one, you're going to need to diagnose the performance problem. The first step is using this framework to diagnose the performance problem that you're having with the model. A robust diagnostic tool is to calculate each learning curve of the loss and a problem-specific metric, like RMSE for regression or accuracy for classification, on a training and validation dataset over a given number of training epochs. Here are a few things to look for. If the loss of the training dataset is poor, stuck, or it fails to improve, perhaps you have a learning problem. If the loss of a problem metric on the training dataset continues to improve and gets worse on the validation dataset, perhaps you have a generalization problem. If the loss or a problem on a specific metric on your validation dataset shows a high variance towards the end of the run, then perhaps you have a prediction problem. So the second thing you need to do is select and evaluate a technique. Review the techniques that are designed to address your problem. Choose a technique that appears to be a good fit for your model and your problem. This may require some prior experience with the techniques and may be challenging for beginners. Thankfully, there are some heuristics and some best practices that work well on most problems. For example, on learning problems, tuning the hyperparameters of the learning algorithm. Specifically, the learning rate offers the biggest leverage. Second, there's generalization problems. Here, using weight regularization and early stopping works well on most models with this problem, or try a dropout with early stopping. And then there are prediction problems. Average the prediction from models collected over multiple runs or multiple epochs on the run to add sufficient bias. Pick an intervention and then read up on that a little bit, including how it works, why it works, and importantly, find examples of how practitioners before you used it to get an idea of how they might solve the problem. The last step is go back to step 1. Once you've identified an issue and you've addressed it with an intervention, repeat the process. Developing a better model is an iterative process that may require multiple interventions at multiple levels that complement each other. This is an empirical process. That means you are reliant on the robustness of your test harness to give you a reliable summary of the performance before and after the intervention. Spend the time to ensure the test harness is robust, guarantee that train, test, and validation datasets are clean, and provide a suitable representative sample of the observations from your problem domain. Hello and welcome back. In this lesson, and the next lesson maybe, let's talk about diagnostic learning curves. A learning curve is a plot of a model, learning performance over time or experience. Learning curves are widely used as diagnostic tools in machine learning for algorithms that learn from a training dataset incrementally. The model can be evaluated on the training dataset and a holdout validation dataset after each update during training, and the plots measured for performance can be created to show the learning curves. Reviewing the learning curves of the model during training can be used to diagnose problems with learning, such as underfitting or overfitting the model, as well as with the training and the validation datasets are suitably represented. Generally speaking, a learning curve is a plot that shows time or experience on the x-axis and a learning improvement on the y-axis. For example, if you were learning a musical instrument, your skill on the instrument could be evaluated and assigned a numerical score each week for a year. A plot of the scores over the 52 weeks is a learning curve that would show you how your learning of the instrument has changed over time. Learning curves are widely used in machine learning algorithms that learn, optimize internal parameters incrementally over time, such as deep learning neural networks. The metric used to evaluate learning could be maximizing, meaning that better scores, larger numbers, indicate more learning. An example might be classification accuracy. It's more common to use a score that is minimizing, such as loss or error, whereby better scores, smaller numbers, indicate more learning, and a value of 0 indicates that the training dataset was learned perfectly and 0 mistakes were made. During the training of a machine learning model, the current state of the model at each step of the training algorithm can be evaluated. It can be evaluated on the training dataset to give an idea of how well the model is learning. It can also be evaluated on the holdout validation dataset that's not part of the training dataset. Evaluation on the validation dataset gives an idea of how well the model is generalizing. So there are 2 parts to this. Training the learning curve. The learning curve is calculated from the training dataset that gives an idea of how well the model is learning, and a validation learning curve. This is a learning curve that's calculated from the holdout validation dataset that gives you an idea of how well the model is generalizing. It's a common practice to create dual learning curves for a machine learning model during training on both the training and the validation datasets. In some cases, it's also common to create learning curves for multiple metrics, such as in the case of classification predictive modeling, where the model may be optimized according to cross-entropy loss, and the model performance is evaluated using classification accuracy. In this scenario, 2 plots will be created, one for the learning curves of each metric, and each plot showing the 2 learning curves, one for the training and one for the validation datasets.